So continuing from where we left off last time we just went through this one supplementary lecture theorem, which it basically says that products of semi-algebras work. And that's my short way of saying that when you have two semi-algebras on two different sets, then when you take the Cartesian product of the sets and collect together all of the Cartesian products of things in the respective semi-algebras, then that does give you a semi-algebra on the new product set. So products work great. Now I'm going to look at this lemma, and we're not actually going to go through the proof, but I want to go through the statement very clearly. So this is just what I found I ended up needing for the next theorem that I'm going to write down, which is about carrying over additive functions to products of semi-algebras. All right, so let's say you have a semi-algebra S. So this lemma doesn't seem to say anything about products. So let's say you have a semi-algebra S of sets on X, and let's say you have a finite collection of sets in the semi-algebra. So F here. Usually when we talk about finite collection of sets, instead of saying a finite subset, like F subset of S, finite, usually what we would say instead is a list like this, S1 through Sn in S, right? But if you write things out like this, I mean, the only difference, it's basically the same thing, but the difference is here you're indexing things. So you're giving them an ordering and you're indexing them, where when you write things like this, you're not indexing, which is fine. I mean, if you want to, any time you can index a finite set. That's what it means. That's actually the definition of finite, right? Is that it's indexable by some collection of natural numbers. By some finite collection of natural numbers. From 1 up through some n. Okay, so one of the challenges with stating some of these things is figuring out when is the right time to index and when will the indexing actually just introduce clutter and get in the way. So when I was thinking about this lemma, I think it made sense not to index here. So let's say that you've got a finite collection of sets in your semi-algebra. Then there's going to be another finite collection of sets. This is the conclusion of the lemma. There'll be another finite collection of sets whose union is the union of your original collection. And these unions, like this union, there's no reason to introduce t in this notation. Actually, you can just write it like this. It's the union of f prime, with not pretending that there's any indexing going on when there isn't. Or this is just the union of f. But when thinking about these things, sometimes it is nice to have a letter that just tends to be the letter that stands for elements of this or that set. So it's purely a psychological aid. And okay, so far it's not saying much, but the key point is the elements of this collection are pairwise disjoint. Okay, so far this is actually looking like something we have said before. This is just saying if you have a finite collection of, if you take a union of finitely many sets in a semi-algebra, then you could rewrite that union as a disjoint union, as a union of finitely many disjoint sets in the semi-algebra. So we've gone through this before. It was actually lemma 1214, where we were saying, if you want to talk about the algebra of sets that a semi-algebra generates, that's the collection of these kinds of things, unions of finitely many things. And then in this lemma, we also pointed out that you can write them as unions of disjoint things. So we've already said that you can do this, but I'm going to add a third point here. By the way, if you wanted to revisit this point, it was lecture 21, part 2 is where it came up. But at this time, I sort of regret making the result then so weak, because we need a little bit more than what this had. So the last point is it should be possible to arrange things so that every element of F, so every component in your original union, is a union of elements of f prime. So that means that f prime is sort of like a finer subdivision. It's comparable to f. Maybe you could call it a refinement of f. So if you think about f in relation to the union of the elements of f, f is like a partition. Not really a partition, since you don't have the disjointness, but f is a way of cutting things up, including overlaps possibly. And then what this lemma is saying is that there is a way of cutting things up without overlaps, and in such a way that you include all of the original slice points that were there. So that's what this last bullet point is saying. How about a little drawing? Let's say that in white here is my union of all of the things in my original finite collection f, which maybe I'll depict the finite collection f in green. This might contain, so there will be some subdivision of this full set. It's not exactly really a partition because there are overlaps possible, right? So these are not necessarily disjoint. So here I'm showing overlaps between two things, but you can have more complicated stuff, right? Like overlaps within overlaps. Let's make the last region. I don't know, how about this? And then a big region in the middle to include whatever I failed to include there. And then maybe, I think I also left this part out. So let's say that these are the various sets S in F. That's what I'm showing in green. So like here's one, here's another one. I hope the picture makes sense. Then what the lemma is saying is that you can replace by another finite collection of sets in the semi-algebra, f prime, so that it's broken apart. So maybe something like this. So they're disjoint, so there's no overlaps between these red ones. And it's broken apart in such a way that if you take any one of the green sets, so this last bullet point is saying if you take any one of the green sets, then it's going to be a union of some of the red sets. So if you just piece together some red sets, you can build up any one of the green sets that you want. Okay, and so on. You know, fill this in. These red fragments are all disjoint from each other. Now, as far as set theory is concerned, of course, it's very plausible to think that you can do this, right? If you take a union of sets, that you can break it up and create this sort of finer subdivision where they're all disjoint and where every one of your original green sets is a union of some red sets. But the key point here is that we're trying to stay inside the semi-algebra. So actually, if you just do what I'm drawing here, that might not work because some of the fragments that I'm drawing out here might actually not be in the semi-algebra. You might have to break them apart further. Break these fragments apart further in order to ensure that they are actually in the semi-algebra. So that's what this lemma is saying that you can actually do. And the extra part that wasn't already in lemma 1214 or in this lecture 21 part 2, the extra part is this third bullet point. So actually that third bullet point, if you follow the construction in the proof of that earlier lemma, then that third bullet point wasn't even true necessarily in that construction. So we really are here requiring a possibly finer subdivision than what was happening back then. So it's really that third bullet point that is adding something to what subdivision we already saw in the proof of that earlier lemma that I mentioned, lemma 1214. And there's a fourth point, which is something very easy and just sort of obvious when you look at the picture, but it's just nice to not have to prove it every time I use it, so I just threw it into this lemma. Whenever you take a green set and a red set that have non-empty intersection, so let's say S is one of the green sets and T is one of the red sets, whenever that happens, and their intersection is non-empty, we have the red set being a subset of the green set. So that's sort of evident there. But of course, should be proven in the lemma. You know, now that I'm looking at this, I actually take back saying that in this picture you have to further subdivide these to ensure that you get things in the semi-algebra. I think that all of these fragments that I'm drawing, at least in the picture, are intersections. The red fragments are certain finite intersections of green sets. And semi-algebra is actually closed under intersections. So I think those really are all in the semi-algebra in the picture. But the challenging thing, if you try to just turn this picture into a proof, the challenging thing, I think, is to try to take the right intersections. Right? You want to take exactly the right intersections. Some of them are intersections of two things. Some of them are threefold intersections. Some of them are fourfold intersections. And you want to collect exactly the right ones in order to get a disjoint union that has these properties. So it's not. So the proof is not actually just like trying to make this picture into a reality. This picture is a little bit overcomplicated. The proof is just by induction, and in the steps of the induction, the behavior of semi-algebras of sets under complements is exploited. I take it back again. You do need to further subdivide, possibly, even in this picture. So here's another picture that makes it more clear. I think my picture was confusing me. So let's say you've got just a union of three sets, like this one, and this one. So like a Venn diagram looking thing with three circles, kind of. In this situation, one of the fragments that you would need to get out of this theorem is this red fragment here. Is this an intersection of a collection of green fragments? If it were, and the green fragments are all in the semi-algebra, then the red would be in the semi-algebra automatically, because intersections of things in a semi-algebra are in there. But no, this red fragment requires some complementing, right? You have to use the complement of this portion. So that's where you need to bring in the feature in semi-algebras that complements end up providing you with further subdivisions that then give you things that are in the semi-algebra. So yeah, interesting lemma, and it's going to be useful in the next fact. So I'm not going to go through the proof of it, just because I feel like it's maybe something you can benefit more from if you read it yourself, rather than me going and explaining the details, although I'd love to. I don't know if you can tell, but I really, really enjoy set theory. Anytime there's a set theory proof, I love diving into it. So this one was a lot of fun. But I feel like I'd be sacrificing progress forward through our measure theory stuff. And I don't want to subject everyone to a technical, notationally heavy proof. So it's an optional read, let's say. But definitely understand the statement and appreciate that this is one great thing about semi-algebras, that you can do this. Okay, before I move on, maybe I'll leave a more memorable, sort of slogan-y way of describing what the lemma is saying. A union of things in a semi-algebra, like the green things being unioned together here, can always be written as a disjoint union, like the red fragments, by further subdivision. So where the original green fragments are actually just unions of red fragments. And it's that further subdivision part, that last bullet point, that I'm really trying to add in as a supplement to what we already had about semi-algebras. Okay, on to the third and final supplementary theorem for this section. So this one is about additive functions and carrying them over to products. So let's say you've got two sets, x and y, and X has a semi-algebra fancy S on it, and Y has a semi-algebra T on it. And define fancy U to be the product semi-algebra. So this is the one that in the previous lecture we saw is indeed a semi-algebra of sets on the Cartesian product, on X product Y. Now suppose you have an additive function mu on fancy S and an additive function nu on fancy T. Then make the following definition. Eta, let's see, from U, the semi-algebra on the product, to the reals, by, and then I just have to tell you what it does to anything in U. Things in U look like this, right? So take mu of S, that's a real number. Take nu of T, that's a real number, and then just multiply them. So define eta like this for all of these possibilities. Man, my script T's are so ugly. I've written so many of them in my life, and I never found a good way to do it. Probably my least favorite script letter. Okay, so here's the conclusion. Then, eta is an additive function, if you do this. So the lemma mentioned back here was for the purpose of proving this. And this I want to look at the proof in detail and get it worked out, because this is going to tell us that when we define our Lebesgue measure, at least the primitive version of it that only operates on finite unions of rectangles to start with, that's actually an additive function. And remember, we need to start with an additive function if we want to go to countably additive in a reasonable way. Like those results that we have that tell us, oh, if you can prove this or that, you get countable additivity, they require you already have additivity. So this is powering that step. Now, one place where you might worry a little bit here with the definition of eta is, anytime you define a function in a way where you don't describe the input as just a variable, but you describe the input as some complicated expression like this. So I'm not telling you eta of S equals and then some stuff, right? I'm telling you eta of and then some complicated expression. Anytime you see this, you worry a little bit about well-definedness, right? So is there an issue here? Well, S product T uniquely determines what S and T must be, right? Except if one of them is empty. If S is empty, then you could vary T here and get the same product, which will be the empty set. But remember that if S is empty, say S is empty, then mu of S would be 0, right? Because mu is additive. We're assuming mu and nu are additive. It's this trick from before, where we say additive, well, the empty set is disjoint from the empty set. So we have this, but on the other hand, it's also this, and algebra, and you get that mu of the empty set is 0. So the only cases where you might worry about well-definedness here, you just get always empty set here and always 0 on the right-hand side. So no problem with this definition. But what is a problem is this additive? That's going to take some bit of effort to prove. And let's put that into the next video.